In the last video, we talked about uh, motion in two and three dimensions. Okay. Now I want to continue that by expressing the right-handed three-pronged coordinate system. So you have your x, y, and z axes. So the reason why it's called right-handed is because the convention means that you can obtain the relative orientation of the three coordinate axes using your right hand. Okay, so to determine the positive directions of the three axes, hold your right hand with the thumb sticking up, straight up, and the index pointer and your index pointing straight out. They will naturally have a 90-degree angle relative to each other. Okay, so by that I mean that we have a right angle here, we got a right angle here, and we have a right angle here. So all of these coordinate and axes all are 90 degrees to each other. So when you see a regular coordinate, when you see regular system, x and y, right here you see a plane, and of course it's 90 degrees with its parent axes. So with that being said, I want to start off by explaining the vectors in 3D can be written just like they are in two dimensions. Okay, so we have our position vector expressed equal to our x, y, and z, x, y, and our z axes, which is also equal to x hat, comma, or I'm sorry, plus y hat, plus z hat. This means that our velocity vector can be expressed as velocity. Oh, sorry, it's not a vector. X component. The velocity is y component. The velocity is z component. The velocity z component is also equal to Vx hat plus Vy hat plus Vz hat. This is called component form. This is component form of the position vector and the velocity vector. So now knowing this, the position vector and the velocity vector can be the change in position over change in time. So using this stuff right up here, I'm going to go say that the velocity vector, okay, is equal to the change in position over the change in time, which is equal to the change in all of this business, x hat, that's going to be red, x hat, okay, plus y hat plus z hat. So if we take the derivative of this business right over here, we get the velocity and the x component. So the velocity in the x component is equal to change in position again, change in position over change in time. Okay. Now we get the change, and the velocity in the y component is equal to the change in the y position over the change in time. Okay. And we also get the z component is equal to the change in velocity, or I'm sorry, the change in position over change in time again, which tells us that if we take the derivative again of the velocity over time with respect to time, we will get our acceleration. So our acceleration is equal to the change in velocity over the change in time, which is equal to the change in the velocity of the x component right here with respect to time. Okay, x hat plus change in velocity in the y component with respect to time, y hat, plus another component, change in velocity, the z component with respect to time, z hat. We can therefore conclude, okay, that the acceleration in the x component is equal to the change in velocity of the x component over the change in time, and the acceleration in the y component is equal to the change in velocity in the y component with respect to time, okay, and z component, the acceleration in the z component is equal to the derivative of the velocity of the z component with respect to time. So with calculus-based physics, this will tell us mostly that we can integrate upwards. So if you just have the acceleration, you can integrate upwards and find your position vector.